In the world of coding, where every line of code holds the power to shape our digital universe, the efficiency of algorithms reigns supreme. Imagine this. You have a critical task to accomplish. Time is of the essence. The performance of your algorithm can mean the difference between success and failure, between a lightning-fast solution and endless waiting. This is
3 hours later.
and we will emerge victorious in our quest for perfect algorithms. First, we've got O of 1, which represents constant time complexity. This means that regardless of the input size, the algorithm's runtime or resource usage will always remain constant. For example, considering this function, it retrieves the first element of a list. No matter how long the list is, the time it takes to get to the first element was always the same. It has a constant time complexity, O of 1. Okay. To identify O of 1 complexity in code, look for operations that take a constant amount of time, regardless of the input size. These operations could be accessing a specific element, performing basic arithmetic, or executing a single statement. Right. Next, let's look at O of log n, which represents logarithmic time complexity. This type of complexity often comes up when an algorithm divides a problem space in half at each step. An example of O of log n is the binary search algorithm. Binary search eventually finds the position of a target element in a sorted list. With each comparison, the search space is halved, resulting in logarithmic time complexity. To identify logarithmic time complexity in code, look for algorithms that divide the problem space in half at each step or reduce the search space exponentially. Alright, moving on. Let's take a look at O of n, or linear time complexity. This means that the algorithm's runtime or resource usage increases linearly with the input size. An example of O of n is a simple function that prints all the elements in a list. As the size of the list grows, the number of iterations in the loop increases proportionately, resulting in linear time complexity. The bigger the list, the longer it's going to take. To identify O of n complexity in code, look for operations or loops that scale linearly with the input size. This could include iterating through a list or performing a linear scan on the data. Basically, it only has to look at the list once. Okay, now look at this mouthful. Linearithmic time. Let's explore O of n log n, which represents linearithmic time complexity. This complexity is often associated with efficient sorting algorithms. An example of O of n log n is the merge sort algorithm. Merge sort divides the input list into smaller sublists recursively, sorts them, and then merges them back together. This divide and conquer approach results in a time complexity of O of n log n, where the n represents the input size. How to identify the O of n log n? To identify O of n log n complexity in code, look for algorithms that divide the problem space in half and have multiple levels of nested loops or recursion. Alright, O of n squared. That one's easy. An example of O of n squared is the bubble sort algorithm, a simple but inefficient sorting algorithm. Bubble sort compares adjacent elements and swaps them if they are in the wrong order, repeatedly iterating over the same list until it is sorted. With each pass, it compares n elements n times, resulting in a quadratic time complexity of O of n squared. To identify O of n squared complexity in code, look for nested loops or operations that involve comparing or processing every pair of elements in the input. Exponential time. This complexity arises when an algorithm's runtime or resource usage grows exponentially with the input size. An example of O of 2 to the n is the recursive function that calculates the Fibonacci sequence. The famous Fibonacci sequence recursively calls itself multiple times, with the number of recursive calls growing exponentially as n increases. This results in an exponential time complexity of O of 2 to the n, making it highly inefficient for larger values of n. Okay, to identify exponential complexity in code, look for algorithms that involve recursion with multiple branches or choices at each step. These algorithms often result in an exponential increase in the number of operations as the input size grows. There you have it. That's big O notation. Can you believe I nearly forgot about factorial time complexity? Okay, factorial time complexity. An extremely inefficient and exponential growth in both time and space as the input size increases. It arises when an algorithm generates all possible permutations of combinations of a set of elements. Identifying factorial time complexity can be done by analyzing the algorithm and its behavior. Things you want to look for: recursion with exponential growth. Factorial complexity often involves recursion, where the number of recursive calls grows exponentially with the input size. Each recursive call explores all possible combinations or permutations, leading to a drastic increase in the number of recursive calls and overall time complexity. Remember to consider scalability and efficiency of your code as you tackle more complex problems. If you have any questions or suggestions, please leave them in the comment below, and don't forget to like and subscribe for more exciting content. Thank you for watching, and I'll see you next time.